Good day! Before you watch this video, please make sure that you have already done the following prerequisites. Good luck! There are many complex parts to vector analysis. However, we're not going to dwell there. We're going to limit ourselves to the very basic. Vectors allows us to look at complex, multi-dimensional problems as a simpler group of one-dimensional problems. We will be concerning ourselves mostly with the definitions. The words may be a bit strange, but the ideas are very powerful. Math and science were invented by humans to describe and understand the world around us. We live in at least four-dimensional world governed through the passing of time and three space dimensions, up and down, left and right, and back and forth. We observe that there are some quantities and processes in our world that depends on directions in which they should occur. And there are some that do not. For example, at the heart of all mathematics are numbers. If I were to ask you, how many burgers did you have? You can say 3, and I would find that answer very perfectly satisfactory. The bare minimum number 3 is a magnitude, and sufficient enough to provide this information that I need. However, if I ask you, how far is your house? And you answered 3, then the information would be insufficient. And I would ask you, 3 what? Evidently, for this question, there are more information that I need. The bare minimum number 3 is no longer sufficient, and I require a denominate number, meaning I require a number with a name. Suppose you answered again, 3 kilometers. The number 3 is now named representing a certain number of kilometers. Such numbers are sometimes referred as scalars. If I were to next ask, how do I get to your house from here? And then you said, just walk 3 kilometers. Again, I would look at you quizzically. This time, not even a denominate, a number with a name, is enough. It is necessary to specify a distance or a magnitude, but in what direction? Mathematicians and scientists refer to these quantities as vector quantity. A quantity which does not depend on direction is called a scalar quantity, and a quantity that depends on direction is called vector quantity. In this episode of Agham Liknayan, Lesson 3, Discussion 1 to 4, you are going to learn how to add vectors using graphical and analytical method. Let's start. So a while ago, we have discussed the definition of a vector in a scalar physical quantity. We're now going to try to elaborate more on that. So as defined, scalars are physical quantities that has magnitude only. When you say magnitude only, these are quantities which has mathematical number and a unit. For example, 3 kilometers, 3 would be the magnitude, while kilometer would be the physical unit. Meanwhile, vectors are physical quantities that has both magnitude and direction. So when we say 3 kilometers, that would be 3 as the mathematical number, kilometer is the physical unit. However, it won't be enough. We should also add the direction. So 3 kilometers would now be 3 kilometers north or 3 kilometers east, and so on and so forth. Now, try to guess the following physical quantities and identify if they are a vector or a scalar quantity. Length is a scalar. Area is a scalar. And volume is also a scalar quantity. If you're going to observe, these are quantities of distances or length. Meaning, it doesn't require us to know what would be the direction of a certain object if we're talking about length. Why? It already makes sense on its own. For example, if we have this and try to measure it, using this ruler, so this would be 15.5 centimeter, and it would make sense already. So it will be considered as a scalar quantity. Again, please try to identify if they are scalar or a vector quantity. Speed is a scalar quantity. Displacement is a vector quantity. Energy is a scalar quantity. So, among this, ang naiba natin would be the displacement. Why? Because displacement is actually a vector quantity. Its counterpart is the distance, which is a scalar quantity. So why is displacement a vector quantity? By now, you should already know because I have given you a link that would actually tell you what's the difference. Temperature, lift, and mass. Try. Temperature is a scalar quantity. Lift is a vector quantity. Mass is also a scalar quantity. Now, why is now mass a scalar quantity? Because mass just defines the amount of substance in an object, so it doesn't require direction. Meanwhile, lift is a vector quantity because you cannot lift something without a direction. The only direction that if you lift an object would be upward, so it should be a vector quantity. There are a lot of other scalar and vector quantities, namely the following. For scalar, we have length, area, and volume, speed, mass and density, pressure, temperature, energy, entropy, work, and power. On the other side, we have vector. We have displacement, velocity, acceleration, momentum, force, lift, drag, thrust, and weight. So those are the list. These are another additional scalar and vector quantities. Aside from being a physical quantity with both magnitude and direction, vectors are also considered as mathematical representations. This mathematical representation represent different physical quantities. Okay, this helps us navigate or interact with abstract concepts such as speed, velocity, acceleration. So, before we actually interact with those quantities, we need to represent them first. And vector has a main role for that. For example, we have the following. I'm going to switch on my full screen view. I'm going to click F11. F11. Ayun niya. There. For example, we have the following situations. So these situations can be analyzed or represented through vector notations or vector representation. Let's choose a pen. Here, a pen. For example, a man is pushing a box. So we can put here an arrow representing that there's a force being applied here. And for example, that would be 3 newtons. Other vector representations would be this. For example, if we have here a positive particle, and if it's a positive, it should emit these electric fields. And these electric fields that I have been drawing are vector representation also. If you have here a ball, and a ball is moving to the left, I put here an arrow, that is also a vector representation. If you have here a car, and the car is moving to the right, another vector representation. So you can see here, those abstract ideas are being represented through a physical medium, which are the arrows. Now, how do we write arrows? There are 2 concepts that would be combined with one principle. First, the length of the arrow signifies the magnitude of the vector. For example, here, we have here a longer arrow. We have here a short arrow. Meaning, in relation to each other, this should be 10 Newton. And this should be about, let's say, 5 Newton. Again, the length of the arrow signifies the magnitude of the vector. Next, the direction of the arrow signifies the direction of the vector. Meaning, if we have here a ball, We have here a ball that bounces for about, let's say, 30 degrees with this reference. If we try to represent that, we should also draw here an arrow there with a 30 degrees angle here in relation to this axis. Now, if we have here this value, for example, it's a cannonball being fired. If that is the angle there, for example, that is 30 degrees also on the x, on the positive x as its reference. If we try to represent that, we are going to draw here, this is the positive x, and this will now be our representation vector, which should be still 30 degrees because our physical object here is at an angle of 30 degrees in relation to the x-axis. Now, combining them, please remember that you can move vectors as long as you don't change its length and its direction. Again, you can move vectors as long as you don't change its length and its direction. Later on, you're going to see how we can use that when we try to solve on different problem-solving questions. We now know how to write vectors. However, we have said a while ago that vectors should have magnitude and direction. Now, how can we illustrate that? By using the concept of unit vectors. Unit vectors is a vector that only has the length of one unit. For example, if we have here the force of 6 Newton, unit vector would have to be multiplied on the magnitude itself. Meaning, we can write here x hat. Then, it can be interpreted as if it's 6n multiplied by 1. Since again, a unit vector is a vector, it should have a direction, but only have one unit. So what would be the purpose of this? The purpose now of unit vector is to define what is now the direction of this magnitude. So in this case, we have a positive x, meaning, if you write it down, 6n x hat, it means that the force is applied on the positive x-axis. So that will be towards east or towards the right. Sometimes, different materials or references uses different letters to indicate unit vectors. In our case, we're going to use the values x, y, and z hat. However, if you encounter a similar reference, I, j, k would also mean the same, indicating the different dimensions. For example, x hat and I hat indicate the horizontal dimension, y and j indicate the vertical dimension, while z and k hat indicates the 3-dimension. Another important topic is finding the component of a vector. In this illustration, we have here a resultant vector. So a resultant vector is the result of the interaction of its component. So in this case, it means this is caused by the interaction of component vector on the x-axis and its component vector in the y-axis. For example, if we have here a metal hoop which is tied on a rope and being pulled in this direction with a force of 4 newtons, and on the other side, it's also being pulled on this direction with a force of 3 newton. We can write here x hat, since it's being pulled on the x dimension. We can write here y hat, since it's being pulled on the y dimension. Now, we can only imagine that this metal hoop will neither go on the y direction and the x direction. It will go diagonally since it's being pulled by the interaction of the x and y dimension. In this illustration, it is safe to say that this vector, this resultant vector, has a component vector on the x-axis with a value of 4 newtons. Meanwhile, on the y-axis, this vector will have a value of 3 newtons. So those are the component vectors of this resultant vector. To summarize, it means that the resultant vector F, resultant, has component vectors fx hat plus fy hat. So this would be your resultant, and these two would now be your component vectors. Properly writing that, we're going to have f is equal to fx plus fy, plugging in the value which we have gathered a while ago. Fx would be 4 Newton x hat plus its y dimension, that would be 3 Newton y hat. So this is now how you write a vector in component form. Now you cannot add these two since they are on different dimension. However, we're going to discuss later how to actually find the value of our resultant vector using our component vectors. What if we want to find out the value of this f? To do that, we're going to use the Pythagorean theorem. First, we have to analyze this illustration as if it's a triangle. So if we have here our value, which is fx hat with a value of 4 Newton, and we have here again its y component with a value of 3 newtons. A while ago, I have told you to remember a certain principle, that we can actually move vectors as long as we don't change its angle and length, or change its magnitude and direction. So you can choose if you want to move fy or if you want to move fx for this image to be completed as a triangle. So in my case, I want fy to be moved, meaning I'm going to move it directly on this side. So this will now be my, so I'm going to use a ruler. Yan. So this is now my fy, which has a value of 3 newtons. Now I can now use the Pythagorean theorem since f is now the hypotenuse of this 2. So applying the Pythagorean theorem, we're going to have f is equal to square root of fx squared plus fy squared. Plugging in the value of fx and fy, we're going to have the square root of 4n x hat squared plus 3n y hat squared. So I'm not going to write anymore the units, so we can have a simpler equation here. So that will now be 16 plus 9. Adding that, we're going to have 25. Square root of 25, we're going to have 5 newtons. So the value of our force here, due to the interaction of fy and fx, is 5 newtons. That's now how you find the resultant vector, the value or the magnitude of the resultant vector, using the value of your component vectors. Okay, let's have some examples. So for this one, we want to find out the component vector of this resultant vector. How do we do that? First, you have to illustrate it. So I'm going to write here an illustration of that f is equal to 15 newtons, meaning this vector force, for example, we have here a cannonball being fired with a force of 15 newtons. Yan. And we want to find out what is now the component vectors of that force. So if this is our vector here, a resultant vector, we should have a component vector which is directed on the x-axis. We'll call that fx hat. And of course, a component vector on the y-axis, we'll call that fy hat. Again, as the principle, we can move vectors as long as we don't change its length and direction. So if this is directed upward, we'll just move it on the other side, but still it's directed upward. For illustration purposes, mapapansin natin na hindi ganong ayos yung line ko, but it serves its purpose. So we're going to have here fy hat. Now, analyzing this, you should have reviewed the SOHCAHTOA. So, if we have been given an angle here which is 28 degree, we have to first analyze if fx or fy is in the adjacent or the opposite side of that angle, which is 28 degrees, or which is this angle here. So let's analyze. If we try to search fx hat, makikita natin that it's actually on the adjacent side of the angle. So we're going to write here adjacent side. Meanwhile, fy is actually on the opposite side of this angle. So that would be opposite. Okay? So from SOHCAHTOA, we have adjacent. So we are going to use the CAH. So C-A-H. Meanwhile, this is the opposite. So we're going to use the SO. So that would be S-O-H. Now, plugging that, we have cosine theta is equal to the adjacent side over the hypotenuse. We'll have here sine theta is equal to the opposite side over the hypotenuse. Next step would be to put our values here in relation to our situation. So we're going to have cosine theta, whereas the theta or the angle is 28 degrees, is equal to the adjacent side. And in our situation, the adjacent side should be our fx. So that would be fx hat over the hypotenuse. The hypotenuse now is our resultant vector, which is f. So we're going to write here f. Let's now go to the fy. We'll have sine theta is equal to the opposite side, which is the fy itself, fy, and then the hypotenuse, which is, again, our resultant vector. Okay, so this is now, we now have to eliminate the f as its denominator. And to do that, we have to multiply both sides by f. Same thing here, multiply both sides by f. Then we'll cancel this, and then we're left with, and then switching the equation, we're going to have this formula in finding the fx. So fx would be equal to f cosine theta. And same thing here, fy would be equal to f sine theta. Okay? Now, plugging in the value, we're going to have f, which is 15 newtons. That would be 15. Cosine the angle, which is 28 degrees. So 28. Then here, we'll have still 15 sine 28 degrees. So please get your calculator and try to find out what are those values. So 15 cosine 28 is, we'll have 13.24. So 13.24 newtons. Don't forget to write the unit and what is the physical quantity it represents. Also, as a rule, if we have numbers na kasunod pa neto, we have to get just 2 decimal values. So, okay na yun. Then, for this one, we'll compute. Fy will now be equal to 15 sine 28. That will now be 7.04. 7.04 newtons. So, these are now our component of a vector for this situation. Problem. So we have here, this time, it's not directed on the x-axis. Rather, it's on the y-axis. However, we're still going to use the same principle. We're just going to point out that hindi laging cosine kapag x-axis, hindi din laging sine kapag y-axis. It would depend on the angle. Again, I would illustrate this by drawing it again here. So this is now our f, resultant vector f, which is a value of 20 newtons. Since we're just focusing on the magnitude, we'll put their absolute value. Then this f has a component vector in the x and y. So we're going to have here the x component fx hat and the y component fy hat. Now, it depends upon you if you want to move fy towards here or fx towards there. So in my case, I'll just move fx since in our last example, fy yung minove natin. So I'll move it here, fx, that will now be fx hat. And the angle for that would be 30 degrees. Doing our strategy a while ago, we'll have to analyze first if fx is the opposite or the adjacent. So in this case, fx hat is actually the opposite side of that angle. Hindi katulad kanina. And we have here fy hat, which is the adjacent already. So that is now the adjacent side. So this is O, opposite. So we'll now have to use the so on SOHCAHTOA on this situation and ka on this situation. So hindi na natin gagawin kanina yung pag-cancel out since you should actually learn how to do that in a gist para mas mabilis yung solving natin since finding out its vector component is the first step pa lang when we try problem solving on more complex topic. So, if this is opposite, we're going to have here fx is equal to the resultant vector. Since this is s, that would be sine theta. S sine theta. Meanwhile, on the other side, this would be fy should be equal to f, the resultant, cosine theta. Again, kung paano natin ito nakuha, please refer to the previous example. So plugging in the value, we have f, that would be 20 sine theta, which is our angle, 30 degrees. And this one, this would be 20 cosine 30 degrees. This will now become 20 sine 30 degree, 10. So this is 10 newtons. So we'll have here a force on the x-axis with a value of 10 newtons. Meanwhile, on the other side, we'll have 20 cosine 30 degrees. That is 17.32. So Fy is equal to 17.32 newtons. So those are now our component vector. Now, if we want to check, for example, if we want to check if this x and y actually are our component vectors, we can use the Pythagorean theorem to find out its resultant. And in this case, it should be 20. So let's do that. So our formula would be f should be equal to the square root of fx squared plus fy squared. That would be square root of 10 squared. So isayin muna natin, 10 squared. We have here 100 newtons plus we'll have 17.32 squared. We'll have here 299.98 since that's 299.982. Square root of 100 plus 299.98. We have now the value of 19.99 newtons rounded off as 20 newtons, similar to our value here. So that's how you check. Again, remember that if you want to find the resultant of a vector, you have to use the Pythagorean theorem. Meanwhile, if you want to try to find out the component of a vector, you have to use the SOHCAHTOA following the angle of your illustration or your situation. Now, we're now going to try to add vectors. The first method we're going to learn is how to add vectors graphically. In this method, you're going to need pen, paper, and a ruler. The first method under graphical method is the parallelogram method. From the term itself, we have to create a parallelogram. To do this, we have to literally copy the two vectors that we're trying to add. So, just a disclaimer, since tinatansya ko lang yung pinaka-arrows ko dito, I'll not be making perfect lines, but the principle should be there. So, please remember that first, you have to literally copy the length of the vector you want to copy. For example, if B has a length of 3 centimeters, if you try to copy B and put it here, it should also be 3 centimeters. Next is the direction. Now, the direction would be reflected as the angle. So, if letter B, for example, is, we have here, let's say, 30 degrees, based on the negative y, and if we try to put it here, and then copy letter B with the same 3 centimeter, again, tinatansya ko lang po, we should also follow its degree, which is 30 degrees here. And this will now be your vector B copy. And same goes for vector A. For example, vector A, with the base of the positive x is, let's say, 40 degrees, and it has a length of 2 centimeters. If we try to copy that, we can put here another copy, and this should be 40 degrees still, using the positive x as the base, and this should also be 2 centimeter in length. Now, to find the resultant vector of A plus B, we just have to connect the origin and the endpoint whereas those copied vectors meet. So this will now be this part, and then up to this part. So this, up to this one. So I'm going to draw that. So this will now be your resultant vector. Now what will now be the magnitude? Since this is graphical method, you have to measure it using your ruler. So since I am doing it electronically, I'm just going to assume that this is about 7 to 8 centimeter, let's say 7 centimeter. So for just for example, so that will now be 7 centimeter. That is now your resultant for this example. Let's try it again. First, we have to copy again this vector D and put it on the tip of the other vector, which is the vector C. We have to copy its length and copy its direction. So assuming, since this is, I'm just going to try to measure my screen. In my screen, that is about 6.5, for example. So letter D is 6.5 centimeter. And letter C is about 6 centimeter. And the angle for that letter D, let's say, basing on the negative y-axis, let's say 20 degrees. This one is about, let's say, 1 degree kasi it's not directed on the positive x. Meron siyang konting angat. Okay. First, I'm going to literally copy vector D and put it on the tip. Put the tail of letter D on the tip of letter C in a while. Then, siguro mga dito siya hanggang dito. Say. Yan. For example, that is now your vector, a copy of your vector D. As you can see, it's not perfect, but you get the idea. You have to literally copy it using your ruler. Medyo mahirap lang when it's on screen. So this is now the copy of vector D. It should have the same size, which is 6.5 meter, and the same angle, which is 20 degrees, using the negative y as your base. Then you now have to copy letter C. Put the tail of letter C on the tip of letter D. I'm just going to tatansyahin ko lang po kung saan po siya. Here, up to maybe here. Okay, so this is now your vector C. This is the arrowhead for vector C. Again, same size, which is 6 centimeter dapat, and using the positive x-axis, which is 1 degree. How we can now find the resultant vector? We are going from the origin of those two vectors that we have added up to the end, whereas those two met. So I'm going to draw that from here, and then dito, here to here. Okay, so that is now your resultant vector. Again, if you try to search the magnitude of that resultant vector, you should literally measure it. So in my case, that would be about 10 centimeter using my screen. So that will now be 10 centimeter. So that's how you add vectors graphically using the parallelogram method. Adding vectors graphically using the parallelogram method has its limitation. For one, we can only add 2 vectors. To solve this, this is where the tip-to-tail method comes in. In adding vectors graphically using the tip-to-tail method, we have to literally move a vector of our choice. For example, if we have chosen vector A as the vector na i-move natin, this one will now change its position from this part up to this part. Now, why is it called the tip-to-tail method? Because the tip of the origin vector, meaning the vector that we did not move, would connect to the tail of the vector that we have moved. In this example, I have chosen vector A as the vector to be moved to the other side. Still following the 2 rules, which is 1, do not change the length because the length signifies the magnitude, and do not change the direction since the direction signifies the angle. So what I'm going to do now is to analyze vector A. First, I'm going to plot here an imaginary Cartesian plane. This is the positive x. And for example, this has an angle of 20 degrees and has a magnitude or a length of about 3 centimeters. That should also be the case when I try to move vector A. So if, for example, I try to move vector A here, I should still have it on a 20-degree angle with a length of still 3 centimeter. Okay? So this will now be erased since I have moved it. Unlike the parallelogram method where you have copied it, on adding vectors using the tip-to-tail, you are going to copy it. In writing the resultant, same as the parallelogram method, we have to start with the origin. The origin would now be the vector that we did not move. And kung saan siya nag-start, that will now be the origin of those 2 vectors that we are trying to add. So meaning, if this is now the origin, now I'm just going to plot kung saan yung mga ito. Okay, for example, this is the part. Sorry, moves. So tansyahin ko na lang. As you can see here, I started at the origin of B kasi nga siya yung hindi ko minove, and I'll end it on the tip of A. So this vector now is my resultant vector using the tip-to-tail method. The magnitude of this one would depend kung what is its physical length. For example, that is about, let's say, 12 centimeter. So that is now the magnitude of this vector if we try to add it using the tip-to-tail method. A while ago, we have stated that one limitation of adding vectors graphically using the parallelogram method is that we cannot add 2 or more vectors. And we have also said that that problem can be answered using the tip-to-tail method. So let's try. For example, we have here your vector A, vector B, and then vector C. We're going to try to add them using the tip-to-tail method. Again, you have to put the tail on the tip of the vector of your origin vector. For example, I'm going to start first by moving vector A. I'm choosing vector B as my origin vector. So I'm going to move A. I'm going to put the tail of vector A on the tip of vector B, still following the 2 principle of length and direction. So first, again, you analyze what's the length. For example, this is 30 degree. This is, for example, about 3 centimeter. Again, follow the length and the direction. So, tansyahan, I'm going to put here a guide. And for example, this is now your moved vector A that would have an angle of 30 degrees and a length of 3 centimeter. 3 centimeter. Now, I have now moved A, so it shouldn't exist here. Na-move ko na siya dito. Now, if we try to move vector C, still same process. For example, this is still our guide. And then I'm going to put my reference angle here. Let's say this is about 35 degrees. And then the length of C is 2.8 centimeter. Okay? I'm now going to move vector C towards this, since this is now our endpoint and not the B. So, tansyahan. For example, this is now our vector C with a length of 2.8 centimeter and an angle of 35 degrees on x-axis as is reference. In writing the resultant, we are still going to follow the same rule. The starting point would be the origin of the base vector, which is B. So from there, you're going to draw up to the end point. The end point now would now be the tip of vector C. So just sketch that out. So from there to there. So this now, kung gaano man yan kahaba, will now be the resultant of vector A, B, and C. For example, that is about 12 centimeter. Nari lang. So that is now your magnitude for R. Please remember that no matter what you move, for example, you choose C as your base angle, you will still have the same result. So let's try. For example, C is your base. So this is your vector C. Then I put A before B. So I'm going to draw here vector A. And then redraw vector B. This one. And then if I try to draw the resultant vector, I'm going to start with the origin, which will now be the base of letter C, up to the end point of B. As you can see here, we still have the same arrow there. Katulad neto. Okay? Try naman natin na A yung base. So this is vector A. Then, we now try to put vector B. So ito yung vector B. Then add vector C. As you can see here, from the origin of our base vector up to the end of vector C, we are still going to have the same result. We're now done on adding vectors graphically. We're now going to move on how to add vectors analytically. When we say analytically, this can be also stated as adding vectors numerically, because we're going to use now mathematical processes as our mean. We're going to analyze the logic or the concept of adding vectors numerically. Since it's numerically and adding vectors, the mathematical process would also always be addition. Now, if we try to add vectors with the same direction, going to the right, we're just going to put here 5 plus 2. we're now going to have 7 newtons directed on the x-axis. However, what if the other vector is actually going on the opposite direction? So this is going to the right and the other one is going to the left. Our mathematical process will now be 5 plus minus 2. That will now be equal to 3 Newton still on the x-axis. Okay, for our first example, we're going to try to find the resultant vector of vector A and then vector B. Vector A has a magnitude of 6 Newton and vector B has a magnitude of 4 Newtons. So let's have some sort of example here. For example, we have here a box, a heavy box, being pulled by a crane towards this direction. That would be vector A, with a force of 6 Newton. And we also have here, it's also being tied by a rope that is directed on this direction with an angle of 30 degrees and being pulled with a force of 4 Newton. Now, what will now be the resultant vector of this situation? First, I suggest you actually take a look at the vectors separately. On our previous topic, I have asked you to find out the component of a vector. We are still going to follow it here. As an organizational process or step, I suggest you create a table of vector forces, enumerating the forces on the x-axis and then the forces on the y-axis. So, the vector forces that we are adding is vector A and vector B, and we are going to add this to produce the resultant vector. Now, we can go about in plugging in the vector forces of A, since if we're going to observe vector A, it's already on the x-axis and it's not directed at an angle, meaning it will have a 0 value Newton on its y, and whatever the magnitude is of vector A, all of that will be directed on the x-axis. That will now be 6n. We now have our concern for vector B. So for vector B, we have to first find its resultant vector, which will be the x and the y, before we can add them together. Now, to do that, we have to separately analyze vector B. So I'm going to draw here vector B. This is now a representation of vector B with a magnitude of 4 newtons and at an angle of 30 degrees. Now, again, just like what we have taught a while ago, vector B is already a resultant vector, meaning it has its component. So that will be component Bx, which means the force on the x-axis of letter B, and component By. Following the principle that we can actually move vector as long as we don't change its length and direction, I'm going to now move vector By in this area. So this is now my vector By. Okay? Analyzing if it's opposite or adjacent on this angle, Bx will now be the adjacent, meaning I should use the Ka on SOHCAHTOA formula, and this By will now be the opposite, and so I'm going to use So on SOHCAHTOA. So if you cannot recall how did we do that, please go back to the previous slides. So finding By, this will now be B, since B is the hypotenuse, and this is SOH, that will now be sine theta. Plugging in the values, that would be 4 sine 30 degrees. Then, going to put here on my calculator, 4 sine, that is now 2 newtons. For x, going to put here B, CAH or Ka, that will be cosine theta is equal to 4 cosine 30 degrees. Computing that, that is 4 cosine 30. That will now become 3.46 Newton. So those are now your X and Y value. Plugging it here, 3.46 Newton and 2 Newtons. So these are now your value. Since they are now on the same dimension, you can now add them because this 6 and 3.46 are all on the X dimension and 0 and 2 are all on the Y dimension. Adding that, we're going to have 9.46 Newton and of course 2 Newtons. However, this process is not yet done. We have to now write its direction. We have now plugged in the value of 2 Newton, which is this one, and 3.46 Newton on this value. However, do not forget to write its direction. For example, 3.46 Newton is a positive 3.46 since if we're going to observe Bx, it's actually directed to the right. So, we can write it as this way, while 2 Newton is directed upward, which means it's also positive. However, please remember, for example, that we have here a value of, if we have an illustration rather, which is directed downward, this 2 Newton will now become 2 Newton. So that will be 0 plus negative 2. So this will now be negative 2 Newtons. For example, again, 3.46 is not directed to the right, rather it's directed to the left. So that will now be negative 3.46 Newtons. So that will be 6 Newton plus the negative 3.46, which will have a value of 2.54. So you're going to have a different result. Okay? So on this juncture, we now have to find the value of R using our previous values. So our value of Rx is 9.46 Newton and our value of Ry is 2 Newtons. Let's write it down. So R is actually Rx plus Ry, which means resultant, which is a value of 9.46 Newton plus 2 Newton. Again, we cannot add these two since they are now on different dimension, unlike the previous setup. So what we're going to do now is use the Pythagorean theorem. So it will be R is equal to the square root of 9.46 squared plus 2 Newtons squared. So let's square first 9.46. 9.46 squared. So we're going to have 89.49 plus 4. Plugging that on the calculator, we're going to have 89.49 plus 4. The answer here would be 9.67 Newton. So the value of our resultant is 9.67 Newton. Now, what if we want to draw that? What if we want to illustrate that vector? So first, we can also use this value. Patansyahin lang natin. So this is a positive 9.46. So that will be directed toward the right. Katulad nito. As our Rx, 9.46. And we also have 2 Newton upward. So mga ganito. So Ry is equal to 2 Newton. Using the tip-to-tail method, from the origin up to the end, we can just draw it here. That is now your R. We can also search the angle using the OA, but we're going to skip that for now since we are just trying to find the resultant. So meaning the value of this force is actually 9.67 Newton. That is now your resultant vector. Okay, for example number 2, as you can see here, we have a different scenario. Both of them are now at an angle. Same strategy, please create your table first so you can be organized in finding your answers. So we have C and D, that would be 2 vector plus the resultant vector. And then of course we have the X and Y dimension. So going to write here X, then Y. We have vector C, we have here vector D, and we are trying to search for the resultant vector. Okay, so let's try to analyze first. We're going to start analyzing first vector D. So to do that, I'm going to separately discuss vector D. So this is my vector D. I'm going to just transfer that image here. Vector D has a magnitude of 3 newtons and it's an angle of 30 degrees. Again, going to illustrate its resultant vector. This will now be dx, dx, and I have here dy. So I'm trying to search the following values here. Again, we can move vectors as long as we don't change the length and direction. So I'm going to move this dy in this part. This is now my dy. Then I'll analyze if it's the opposite or adjacent. So dy, as you can see here, is the opposite of 30 degrees. So that will be so katawa. So my value here would be d so. That will now be sine theta. Meanwhile, dx is adjacent. So that's ka or cosine theta. So that will now be d cosine theta. So these are now my formula in finding the x and y components. So let's try. Let's start first with dx is equal to d. That is a value of 3 cosine 30 degrees. The answer there would be 2.60. So 2.60 newtons. That's the value of dx. Meanwhile, dy, that would also be 3, but it will now be sine 30 degrees. Solving that, that will be 1.5 Newton. This time, before we actually put it here, what we're going to do is to analyze already its direction. So dx, if we're going to look at its illustration here, it's actually pointing to the right. Meaning, this answer here should be enough, and we can put it directly here as 2.60 newtons. For dy, we also have that same value, same sign, since it's also directed upward. So we can write here 1.5 newtons. Okay, so that will now be the value of our dy, of our d and its component. Analyzing vector c, as you can see here, it's quite tricky since nasa 20 degrees siya. Okay, we can do that. However, we have to follow the same base here. So we can create an angle here just by adding these two. So same x-axis here. So this will now be 50 degrees. C is equal to 5 Newton. This is now Cx, and again, you'll have Cy. Moving this vector here, Cy. Analyzing through SOHCAHTOA, this is now the opposite, and this is now your adjacent. Okay, going directly to our formula, dx will now be adjacent, so ka. That will be d cosine 50 degrees. And dy will now be d so or sine theta, sine 50 degrees. So let's try to compute that. So d has a value of 5. So 5 cosine 50. So that's 3.21. So we'll have here 3.21 Newton. Then still 5 sine 50. Sorry, sine 50. That's 3.83. 3.83 newtons. Now, plugging this value on our table, Cx will now be, so this should be C, should be C. So Cx will now be 3.21 Newton, and then Cy will now be 3.83 Newton. Okay, still they are both positive. As you can see here, short version is that C is on quadrant 2, whereas the value should be of the x and y will be positive, positive. Adding those, we have 3.21 plus 2.60. We'll have 5.81 and 3.85 plus 1.5. That is 5.35. Okay, these are now our value of our Rx and Ry. Writing it down in component form, we have Rx plus Ry, plus Ry. That will now become 5.81 plus 5.35 square root of the squared since we want to find the value of r, square root of 5.81 squared plus 5.35 squared. The answer there would be, this is 33.75 plus 5.35 squared, that is 28.62. 28.62. Now, the value for that would be 7.898. So that will be 7.90 newtons. So that will now be the resultant value of your R. So R is equal to 7.90 newtons. So this is now your answer for the resultant vector of this illustration. Now, ano ngayon yung magiging itsura niyan? Again, please go back here. That would be 5.81, about 6 for example. Tansyahin lang natin. This is now your Rx. And 5.35, about the same size. So this will be our Ry, meaning this is now your resultant vector with a magnitude of 7.90 newtons. So for example number 3, we're going to try to solve this problem. An unknown particle is moving 5 meters per second to the east, and then 8 meters per second southwest. We want to calculate the resultant velocity of the particle. So it's better again to first illustrate that. It's moving 5 meters per second to the east. So this particle is moving 5 meters per second to the east. So that's a velocity of 5 meters per second. And then 8 meters per second southwest. So after this, it moves 5.8 meters per second southwest. So dito yun banda. Yan. We're going to illustrate it as a bit longer than 5 since it's 8. So that will be 8.00 meters per second. That will now be velocity 2. Calculate the resultant velocity of the particle, meaning we have to calculate its resultant vector. Now, katulad kanina, we can create our table here. We have two vectors, that velocity 1 and then velocity 2. And we're going to have here our resultant velocity. Divided into 2 dimensions, that's the x and y. You have v1. Then we have v2. For v1, it's pretty much straightforward since it's already east, meaning that it's on the positive x. So this is already 5. Wala siyang y component, so that would be 0. However, our situation would change if we try to find the component vector of v2. So I'm going to isolate v2. So this is now your v2, 8 meters per second. Now, I can choose any angle. Pwedeng dito naka-base sa negative y or pwede rin sa negative x. I'm going to choose negative x. It's on the southwest, meaning it should be half of a 90-degree angle. So this should be 45 degrees. So that's now your angle. So v2 is now 8 meters per second with an angle of 45 degrees. And then, finding the x and y, we have here our v2x. It should be negative since it's directed towards the left or the negative x-axis. Di pa natin alam kung anong value yun. We're going to find it later. And then, we'll have here, again, a negative y since it's pointing downward. So this will now be our v2y, but still, we don't know the values there. We're still going to use the SOHCAHTOA. So for our last example, we'll have this. An unknown particle is moving at 5 meters per second east, and then 8 meters per second southwest. Calculate the resultant velocity of the particle. So basically, we have to find out its resultant vector. So let's illustrate that first. Sabi, meron daw tayo ditong particle, and it's moving east. So this is the illustration for that. It has a velocity of 5 meters per second. Afterwards, it moves 8 meters per second southwest. So that will be here using the tip to tail method. And it is now significantly longer since it has a higher magnitude than 5. So let's call this V1 and then we'll call this V2. 8 meters per second. So what we're going to do now is use the same strategy. We have to first create a table to allow ourselves to organize our values. That would now be divided into 3. The vector forces, which would be V1 and V2, and of course, the resultant vector. We have x and y dimension. So we have V1x, V1y, V2x, V2y, Rx, and Ry for their components. We can actually just plug in the value of V1 here since it's directed east, meaning it's on the positive x dimension. So we're going to put here 5 as 5 meters per second and 0y since it has no y component. But for V2, we're going to have a different scenario. So I'm going to illustrate V2 again here. V2 is going on this direction, meaning if we try to do a tip-to-tail method, it should have a component vector which is directed towards here. And it's on the x-axis, so we'll call that V2x. V2x. And it will also have a y component since you can see here it's going downward. So, still tip-to-tail method. And then we'll call this V2y. What will now be the angle of our V2? Basing on the negative x, we're going to have here our angle. And from this direction given to us, southwest, it should now be in the middle of south and west, whereas the south and west is a 90-degree angle. So the half of that will now be 45 degrees. So our theta here, theta will now be 45 degree with a magnitude of 8 meters per second. We now have to search the component of V2 in its x and y, or we have to search for V2x and V2y so we can put here on the table and now we can add them. So to do that, we're going to still use the SOHCAHTOA. First, we have to analyze what part of the triangle would be V2x and V2y. So for V2x, we can see here that it's adjacent to the angle. So V2x is adjacent to the angle. So using SOHCAHTOA, here, this would be ka, meaning it should be cosine. That will now be the shortcut. Now, basing on our knowledge or information a while ago, the formula here would now be V2x is equal to the hypotenuse, which is V, to ka, that will now be cosine, and then theta. Plugging in the value, that will now be 8 cosine 45 degree. So the value of our V2x is 8 cosine 45. That is 5.656. So 5.66. 5.66 meters per second. Now, looking at the illustration, V2x is actually directed to the left or to the west. So this would be negative, meaning our value here would be negative 5.66 meters per second. So that is the value of our V2x. So we can plug it here, negative 5.66. Now, solving for V2y, let's put it here, V2y. It is now on the opposite of the angle. As you can see here, it's now on the opposite of the angle. So we have to use SO in the SOHCAHTOA. So that will now be V2y is equal to v2 sine theta. Now, the angle is 45 degrees, so they should have the same value. But for computational purposes, we're going to do it still. 8 sine 45 degree. And again, that should be 5.66 also. So 8 sine 45. And there it is, 5.66 meters per second. So that will now be our v2y. Now, what will now be the sign of this? So still, v2y, as you can see here, is directed downward. So that will now be the negative y-axis. So this should be negative 5.66 also. So this is negative 5.66. Okay, now we have our value of our v2x and v2y. We can now add the following vector forces on the same dimensions. So this will be negative 0.66. This will be on negative 5.66. Remember that you have to add. So this would be 5 plus negative 5.66. This will be 0 plus negative 5.66. This is now our resultant vector in component form. So if we want to illustrate that, so this is the x-axis, it's negative 0.66, about this size. And we have negative 5.66, so it will be about this size. So this will now be our v2x. This will now be our, this will now be our r2x. Rx, this will now be our ry. And the resultant vector itself would be this image here. Okay? So what will now be our value of that resultant vector? Since ang pinapahanap sa atin is calculate the resultant velocity. Now, we all know from the previous video that we are now going to use the Pythagorean theorem. We're going to have r is equal to the square root of rx and ry squared, rx squared plus ry squared. So, plugging in the value, we're going to have 0.66 and then 5.66. Now, pwede natin hindi lagay yung negative since it will be squared din naman. So, let's write here 0.66 squared plus 5.66 squared. Okay? So, computing that will be square root of 0.66 squared plus 5.66 squared. Value there is 5.70 since it's 5.69. So 5.70 meters per second. So that is now the value of our resultant velocity. So this is now your final answer. We can still search for the angle here, but ang tinanong lang naman sa atin would be the resultant velocity. Before we end this lesson, let's try our knowledge. Please answer on your own. These are physical quantities that has both magnitude and direction. Answer is vectors. Next, these are physical quantities that has magnitude only. Answer is scalars. Length, volume, and area are examples of physical quantities which are scalars. Next, displacement, momentum, and force are examples of vector quantities. These are mathematical representations of physical quantities that has both magnitude and direction. Answer is very good. Next, the length of the arrow signifies the direction of the vector. Now, is it true or false? This? False. The direction of the arrow signifies the magnitude of the vector. True or false? Very good. The length of the arrow is actually the magnitude of the vector, while the direction of the arrow is the angle or the direction of the vector. Last one, we can purposively move vectors as long as we don't change the length. in the direction of a vector, true or false. Very good. That would be all for our first pre-recorded video. I hope you have achieved our objective, so by now you should already know how to add vectors using the graphical and analytical method. See you next time.